So in a few days, the Nobel Prize in Physics is going to be announced on the 6th of October. And I thought I'd make a little prediction as to who the eventual winner might be. Now, I have to say that there are no open nominations, so nobody knows who's in contention. So this is complete guesswork. But I'm going to guess that first, it's not going to be an astrophysicist, because a bunch of astrophysicists won last year. And I think it's going to be someone from the realm of quantum information. Specifically, I think it's going to be Aspect, Clauser and Dellinger's team for their work on the Bell's inequality. Before we get to Aspect et al., we need to understand a little bit about quantum physics. Now, in quantum physics, there's a concept called wave-particle duality, which means that things that you think of particles are also waves, specifically probability waves. Now, let's step a step back. If we have a fundamental particle, a photon or electron or something, and let's say they have a quantity called spin, we can think of spin as something like angular momentum. It's not exactly spin, but for the purposes of this video, let's imagine that it is. Now, you can spin this way or you can spin that way, and so the vector of angular momentum will be either pointing up or down. Now, in quantum mechanics, why do we call this wave-particle duality? Is because until you make the observation, you do not know which spin it is. And the strange thing about quantum mechanics is actually the particle exists in a superposition of spin states. It's both states simultaneously with a probability of being in one or the other. And that's the probability wave of the wave-particle duality. Now, why are we explaining this? Well, imagine you create two particles out of energy, which is possible in quantum physics. Now, the angular momentum of the universe must be conserved, so they must have opposite angular momentum, or opposite spin. Now, that means that I create two particles. If I shoot this particle over to that end of the universe, and shoot this particle over to that end of the universe, and I measure one of them, and I measure an upspin here, that means that this must be a downspin here. But remember, part of quantum mechanics is that we didn't know which spin state they were. Not that we didn't know, it's that fundamentally the particle is in both spin states simultaneously. So it's not just a case that we just didn't know, we haven't observed yet. They are actually in both states at the same time. The implication is that as soon as we measure here, and we know this is an upstate, we break down its wave function, somehow, and this is what Einstein's thought experiment I'm explaining right here, somehow that information got transmitted all to the other end of the universe until this guy, it needs to be in a downstate. Einstein looked at this and he said, well, that can't possibly be the case because surely you are transmitting information faster than the speed of light instantaneously across the universe, which we know is not possible. And he called this spooky action at a distance. He hated this quantum mechanical effect. His explanation was something called hidden variables, that actually, like in classical physics, as these particles were created, they knew what their spin states were. There was no superposition of probabilities. They were an upstate and a downstate, it's just that we couldn't access it, we couldn't measure it. And so they were an up here and a down here all along. There was no transmission of information. But the true quantum mechanics explanation is called entanglement. Entanglement means that both particles were in both states simultaneously as they traveled to other ends of the universe. It was only when you made the observation here, and by making that observation, collapsing the probability function into a single state, the upstate, that this then became the downstate. And that is a fundamentally different paradigm of physics. And this was argued about for years and years and years. Now, what happened later, many years later actually, was that a physicist called Bell, an Irish physicist, came up with something called Bell's inequality. Now, Bell's inequality sought to distinguish between the two possibilities, the hidden variables of Einstein and the true quantum entanglement explanation. Now, I won't get into the maths here, but basically the conclusion is that Bell came up with some kind of experimental configuration that if you did it, you would expect to measure a different result if the hidden variables were correct, and you would expect a different result if the quantum entanglement theory was correct. Aspect and his team were the first set of experimental scientists to prove, or disprove actually, Bell's inequality. In other words, they were the first scientists to prove that the quantum entanglement explanation is correct and there are no hidden variables. Now, this is an earth-shattering result really, because what it's telling you is that the very core foundation of quantum mechanics was tested and proved to be correct. The strange quantum interpretation of the universe is the correct interpretation of the universe. So you're kind of throwing out classical mechanics now, and that's why it was such a big, impactful result. Later on, applications of quantum entanglement and so on have form foundational parts of quantum computers and so on that we talked about at the start of the video. But the reason I think Aspects et al. Deserve this Nobel Prize is because the significance of that experiment is hard to overstate in terms of cementing the very foundations of quantum mechanics and moving us away from the classical position that was advocated by Einstein and his other colleagues for so long. On the 6th of October, I'll be doing rapport with another colleague on Bhutan, where we'll discuss, well, who the Nobel Prize winner is, the significance of the research that eventually wins. Of course, we don't know what that is yet. Together with a lot of other cool things like previous Nobel Prize winners, the impact of previous Nobel Prize work on day-to-day life, and we'll also give some insights into our own careers in astrophysics and physics and beyond. So it'd be great for you guys to join us. I look forward to seeing you there on the 6th of October and to see whether my prediction of this year's winner is accurate.